Well, welcome everyone to the second talk of the afternoon session. So the second speaker is Lior Silberman, and he'll talk about scattering of quasimodes. Lior.
Thank you, Dima, and thanks to the organizers for inviting me. So I'm going to report on joint work with Suresh Eswarathasan, who's now at Dalhousie University. So he's in Canada now. So this is, I guess, a slightly different flavor than what we've had earlier today, but I think there's other speakers who might be also discussing related things. So, the talks this morning were kind of about how we can get the geometry out of the spectrum. And this talk is more about, in some sense, the converse direction of how the geometry affects the spectrum and how in particular, through the dynamics. So the geometry of our manifold affects the dynamics of the geodesic flow, and that affects the spectrum because the eigenfunctions have to somehow respect the geodesic flow. And this is what this work is trying to probe. So let's start with a picture, which is in some sense what we're trying to understand, though not in this flat setting. So, 1980, this is Heller in 1984. I'm sure many of you have seen this picture before. This is a planar domain, the Budimovich Stadium. It's a cylinder with two semicircles, semi-discs, I should say, added. It's a rectangle with two semi-discs glued on the sides. You take the flat Laplacian with boundary conditions, and you compute the eigenfunctions. And mostly they seem, if you plot sort of darker means the amplitude of the oscillations is larger. Mostly they seem most uniformly smeared. But occasionally you see pictures like this. And what it seems is that these pictures are enhanced along some closed trajectories of the geodesic flow. In other words, closed biliar trajectories in the plane. And the kind of question, the quantum unique ergodicity question is the extent to which this happens in various settings. So you can ask, to what extent, Egorov's theorem says that on some level, once you micro-localize, eigenfunctions have to respect the geodesic flow. And the question is, to what extent can eigenfunctions get enhanced in this way? And to what extent this is just a kind of a law of small numbers effect, where if we computed much higher eigenfunctions, this would be wiped off and we couldn't see it. And related to this, a question of formalization. So how do we formalize the way we see this picture? In what sense do we mean that these eigenfunctions seem enhanced in these various trajectories, right? Let's say in this trajectory here, or in these trajectories here, or maybe in this trajectory here. What does it mean to be enhanced, right? You can measure in the kind of sharpest, you can look at the L infinity norm, which in some of the ways the weakest possible enhancement, right? It could be large on this point, and then it could be large on some point, and then small in the neighborhood. And you can look at it at the kind of some LP norms. And you can also look at restriction bounds, restrict to the set, compute various L2, LP, or various other bounds. And we will look at the strongest possible sense in which this phenomenon occurs, which is that there's positive mass near these orbits. That is, if you take an epsilon neighborhood of one of these orbits and you computed the L2 mass of the eigenfunction, maybe that could be made large, meaning for every epsilon, this mass would be large independent of epsilon on some subsequence of eigenfunctions. Okay, so this is for true eigenfunctions. What happens? So the goal of this talk is to explore approximate eigenfunctions. So let me state the theorem, and then I will discuss the plan of the talk. So we're going to specifically take the most symmetric case because it's the easiest case to calculate. So we take a compact hyperbolic manifold of some dimension little n. I guess I'm using little n for something, but let's take a compact manifold of any dimension, take a probability measure on the unit tangent bundle invariant by geodesic flow. And then then we're going to probe this question by not looking at exact eigenfunction, but looking at approximate eigenfunctions. And what we'll show is that if you take an approximate eigenfunctions in the log scale sense, something like they say the spectral support is of width square root lambda over root lambda, or in the sense here, it's more or less the same because you can do spectral cutoffs. Then the appropriate microlocal measures, the natural lift of the natural measure of the eigenfunction to the tangent bundle, converge weak star to your favorite measure invariant by geodesic flow. So for example, yes, you could take a closed geodesic and get a sequence of approximate eigenfunctions that concentrate near the closed geodesic. Okay, so the goal of the talk, first of all, I'll explain why a result like this should be interesting, and then I will discuss the kind of main technical part of the proof, which is how to do this on hyperbolic submanifolds, and then I'll briefly mention the diagonal argument that gets you from hyperbolic submanifolds to a generally invariant measure. And if you have questions, don't hesitate to interrupt me or put something in the chat. And right.
So the size of those quasimodes is somehow the smallest possible in some sense, right?
Probably yes. So
like at least some people, I don't know, you or some people in Israel, right? For Eisenstein, if the quasimode is too small, you don't have this non-uniqueness.
So, okay. So if the quasimode is, okay, if you take something which is little o of root lambda over log lambda, then there are two results that would say that something like this, literally speaking, cannot be true. One of them are the positive entropy results of Anantha Raman and so on, which would put an absolute lower bound on the entropy and therefore on the possible limit measures. And the other is the breakthrough of Dyatlov-Jin,
right?
Which should in principle apply to such quasimodes. I'm fairly certain it does, if you take little o of root lambda over log lambda, and at least for surfaces in 2 dimensions. And it would show that the limit measure has full support.
Yeah, okay.
Which is a different abstraction.
Okay, thank you.
But for example, I wouldn't know if quantum unique ergodicity is true for little o of root of 1 over log lambda quasimodes.
Okay, thanks.
Okay, so first of all, I'm going to switch to semi-classical formalism. I guess I come from physics. It's in some ways it's easier to think about it this way. So instead of thinking about eigenfunctions of Laplacian with the eigenvalue going to infinity, I'm going to add this parameter h bar squared. And so in some sense, the eigenvalue E is going to be fixed and h bar is going to go to 0. I just shifted the eigenvalue to the other side. And then I'm going to take I also want to microlocalize. So to every function A on the unit cotangent bundle, I assign the appropriate pseudo-differential operator with symbol A with respect to your favorite quantization. For those who are not used to this kind of picture, if we merely think about what happens on the surface itself, then this operator just means, and A is just a function on our surface or in our manifold, then this operator just means to multiply by A, and therefore the inner product we have in this picture just means, so here, if A is A of X on M, then mu of A just means you take the integral on M of absolute value of the eigenfunction squared times A d volume, right? So, but we're generalizing this to functions on the unit cotangent bundle. And then the Egorov's theorem says if you take the limit as h bar goes to 0, then the limiting measure, if I take exact eigenfunctions, is going to be invariant by geodesic flow. Of course, the individual ones are approximately invariant, the individual measures here, and their weak star limits have to be invariant. And the question is, as I said before, if I take eigenfunctions, what kind of weak star limits do I get? So Schneermann's theorem says that if the geodesic flow is ergodic, that's the geometry going into the spectral theory, then we have a subsequence of density 1 of the sort of Weil says we have lots of eigenfunctions, and Schneermann says if you take there's a subsequence of density 1 where the limit is the obvious measure on the cotangent bundle, the Riemannian measure of the cotangent bundle on the energy surface, the unit cotangent. Okay, so in other words, one measure we know we get, which is the obvious measure on the cotangent bundle, and we ask ourselves, are there these low density eigenspaces that sequences that Heller found, these rare eigenfunctions that do something different. So Rudnick-Sarna conjectured that this doesn't happen in negative curvature. That's the quantum unique ergodicity conjecture. And in some sense, that's what we're trying to probe. Right? So we're trying to probe the conjecture that says that actually these kind of scars Heller observed numerically in the Bunimovich stadium, at least in the measure theoretic, in the weak star sense, in the worst possible sense, do not occur in negative curvature. Yes, I should. Okay, so this is the problem. As we said, we want to take the weak star limit, so the eigenfunction. So let's view some historical results. So as we just said, in negative curvature, where the geodesic flow is ergodic, the Schnirelmann's theorem says that the Liouville measure occurs. And the Rudnick-Sarna QUE conjecture says it's only measure. And then Anantharaman had a major breakthrough about 20 years ago with follow-ups with several co-authors that put a strong restrictions on the positive limit. So we're not going to discuss what positive entropy means. It's a term from dynamical systems, but it's a measure of the complexity of the measure. You can think of it as somehow as dimension of the support. That's not quite true, but it's related to that. So for example, if I take a totally geodesic hyperbolic submanifold, and I take the obvious singular measure supported on that hypersurface, the volume measure of that hypersurface, the Hausdorff measure, then the entropy of that is the dimension, is proportional to the dimension of the hypersurface. So, so for that reason, you can think of it as a measure of dimension of the. It's more or less the dimension of the support. That's literally true if your measure, in many ways, if your measure is ergodic, but otherwise it's not quite true. So, but anyway, this is a strong restriction. And in constant curvature, it says that in some sense we get at least half of Liouville measure. But still, this is this is not a complete. This is not this leaves a lot of room, because you can get half of the complexity of Liouville measure in some sense in two different ways, in many ways, but at least two. You can take a measure which is a convex combination of half of Liouville measure, which gives you half the complexity, and half of something really simple, like a closed. Or you can take a measure whose support is half the dimension, right? Either of those would have half the entropy. Okay? And there's a whole zoo in between, including fractal measures, measure of fractional dimension. One special case where there was a lot more progress was the work of Lindenstrass, which showed that if you add additional symmetries, if you take boundary conditions, which are not just periodic boundary conditions of the compact manifold, but also that have additional symmetries, number theoretic symmetries in the boundary conditions, so-called Hecke operators, then the joint eigenfunctions actually become equidistributed. And so Lindenstrass proved this for compact hyperbolic surfaces in the congruence case. And with Venkatesh, we generalized this to some higher rank symmetric spaces. And again, a key role is played by this constant of entropy. Sorry, here. On the other hand, it turns out that sometimes equidistribution doesn't work. Sometimes, when we say equidistribution, we mean all the eigenfunctions are roughly, in root mean square sense, look like constant. So first of all, in the Bunimovich stadium, Hassel in 2008 kind of confirmed this observation by Heller. He showed that if you choose the width randomly, then with probability 1, equidistribution fails. The trajectories he found are not the unstable ones that are in the pictures, but the stable ones, the bouncing ball mode. Okay. A different direction of tri-negative results is saying, what happens if I allow approximate eigenfunctions? And of course, if you allow the spectral width large enough, you can approximate any function you want by a combination of eigenfunctions. And so you can get any limit you want. So you need to somehow restrict the spectral width. So I'm going to say that I'm going to define log scale. This is the this is the semi-classical picture version of the condition we had in the beginning. So this is square root lambda over log lambda, just written when we write the eigenvalue with respect to this h bar. So first of all the theorems with microlocal calculus can work with these quasimodes. So the weak star limits are still positive measures. Egorov's theorems still apply, and the weak star limits of these measures are still invariant probability measures, which concentrate on the unit cotangent bundle. And the question is, what measures do we get? In fact, Anantharaman's original paper actually addressed this question and gave an entropy bound, which was positive if your if your quasi-mode is close enough. So for some constant C, depending on the manifold, C0, let's say if C is less than C0, then the entropy is still positive. Right. And recently, Swaratha-san, under some technical condition, managed to improve this bounds using the later technology of an Antharaman Koch and an Antharaman non-Macher Koch and an Antharaman non-Macher. Okay. But in a different direction, Brooks in 2015 on hyperbolic surfaces managed to construct quasimodes that do not become equidistributed, that concentrate on closed geodesics. Right? And this is what we want to think about here. So again, take a hyperbolic surface, take your favorite closed geodesic on it. Right? We've seen this picture in the picture with a pair of pans. This morning we discussed to assemble a surface from pairs of pans. So take one of these cuffs. Take one of these closed geodesics on which we like to take the surface. So you can make approximate eigenfunctions that concentrate just near this cuff. So that in the limit, the measures converge weak star. So these, of course, highly oscillatory functions, but in the root mean square sense, they concentrate to the delta measure around this closed geodesic and nowhere else. And if you lift the cotangent bundle, yeah, they actually go only the direction along the geodesic. Okay. So, now our result is a generalization of this. So as we discussed before, I'm going to mention something about the proof, but this theorem we stated earlier is a generalization of Brooks' result to higher dimensions, right? When we say, first of all, you don't have to work on a surface, you can take any hyperbolic manifold. And secondly, you don't have to concentrate on a closed geodesic. You can concentrate on any invariant measure. And now let's compare the positive result of an Antharaman and the negative result, if you want, an Antharaman or an R positive, or depending on which one you call positive, which one you call negative, depending if you like non-concentration or you like concentration. But in any case, an Antharaman's method and the improvement of Swaratha-san give a dependence of the entropy limit on the spectral width of the quasimode. Our result gives explicit dependence when the limit is a totally geodesic manifold, but not in other cases. So again, so more questions. Okay, so let's try to say something a little bit about the proof and why it's easier to calculate in the hyperbolic. So again, we have a hyperbolic N manifold capital N. We have a totally geodesic submanifold capital M. Our goal is to construct eigenfunctions on the big or approximate eigenfunctions on N that concentrate on M, right? So they will oscillate with large frequency on M and near it, and then they will decay rapidly away, right? That's the thing we're trying to construct. And the D will be the codimension. And our goal is to show that if you want to work depending on how big the codimension is, what spectral width we need in the quasimode to make this happen. Okay. So now why is it useful to work in this technology? Because at least locally speaking, this setting looks like a warped product, right? So if you think of things along the submanifold M and in perpendicular direction, then the hyperbolic metric looks like a warped product. It looks like the metric, when you work on parallel sheets, if you take the kind of parallel, right? If you work perpendicular in parallel sheets, then the metrics on these sheets in the right coordinates, you take the obvious decomposition of the Lie algebra, are the hyperbolic metric on the kind of exact totally geodesic submanifold, but they're warped by a scale factor. And what this gives us is that in those coordinates, what does the Laplacian look like? Our Laplacian is the Laplacian on the submanifold with a scale depending on the distance from it, right? R is our radial distance. Then there is a flat Euclidean Laplacian in the perpendicular coordinate. And then there is some further terms which are largely harmless. R again is the radial direction in the perpendicular, the radial in the perpendicular. So X is an RD, right? X is, you can think of X as D Euclidean variables. R is the radius vector along X, right? And we get these operators. And so we take an ansatz, we take something which is on M, is an eigenfunction of some type. And then we try to understand what we do in the perpendicular direction. I guess, sorry, it's the other way around. Phi here is the eigenfunction on M, right? Phi we take to be an exact eigenfunction on M, let's say. And then we try to do something clever in the direction X, right? And the goal is for this something clever to decay rapidly away. I mean, the game is to find this eigenfunction, this object C, that at the same time will give us rapid decay in the X direction away from the singular set on which we want to concentrate. And on the other hand, still keep the whole ansatz an approximate eigenfunction. Now, if you plug this into the formula here, you see that if you compare the hyperbolic Laplacian on the big manifolds to the eigenvalue in the ansatz, we use the same eigenvalue, then what you get is in the M direction itself is just the eigenfunction, etc. We can really separate the variables, but in the perpendicular direction, we get some operator H, and the operator H actually looks very much like a Hamiltonian for an inverse harmonic oscillator. We have a Euclidean Laplacian, we have a potential, which if you do a Taylor expansion looks like the inverse harmonic oscillator. And then we have two terms here which decay with H bar and are negligible in the limit H bar going to 0. So, and this is basically the end of the argument. And this part is not, I mean, kind of the observation that in hyperbolic situations, if you decompose things like this, you should get something like a sort of near a hyperbolic fixed point. You get an inverse harmonic oscillator in the appropriate coordinates is not new, of course, though usually it was in a situation where the perpendicular is one dimension. So this is not new. You can find it in works of Zvorsky and others, but it's convenient to work explicitly. In general, you can get something like this in greater generality. For example, Esvarasasan and Nonan Masher managed to get the same thing in variable negative curvature if you take a hyperbolic, or even if you take a geodesic, which is where things are hyperbolic on the geodesic, regardless of what the metric was elsewhere. Okay, but again, our goal is to take this approximate inverse harmonic oscillator, find an approximate eigenfunction, which is actually approximately killed by this, and it's concentrating near the origin.
Lior, it's about like 1-2 minutes.
Yes. So so I'm going to skip the microlocal technology that does it. This is more or less standard once you switch the right symbol to the, basically, if you do a correct change of coordinates in the quantum system, so you have to do sort of not just in the classical system, which is easier, then you can make it to be exactly an inverse harmonic oscillator, and those have the nonas. Okay, so let's ignore step 3 that you start with how to do this, and you take this construction, you cut off to a color around and you're done. So what have we done so far? We've shown that if you take this manifold N, you take this submanifold M, which is totally geodesic, you take a sequence of eigenfunctions from Schnirelmann that concentrate on the totally geodesic submanifold. Eigenfunctions on the totally geodesic submanifold that concentrate there. Then you extend them using in the normal direction by these inverse harmonic oscillator eigenfunctions, and the whole thing becomes approximate eigenfunctions that concentrate on for the measure on the. Now, what can we do more? So the thing you could do more is to check that in fact nothing we did so far really depends on M. Meaning the spectral width that we needed to make this work depends on the codimension. But it does, I mean, and of course there's constants in the proof that depend on M, but none of these constants go in the spectral width. Yeah. And so since nothing depends on the spectral width, you can take a diagonal argument where you take a sequence of submanifolds M where the hyperbolic measures on those converge to some other, maybe even fractal measure. And then you take a diagonal argument. You have your quasimodes converging to each of them. You go on the diagonal and you get the limit measurements. And that's the end of the argument. I should say that the problem with this is that the spectral width we need, the natural thing to do is to take geodesics, but then we need the full spectral width for the geodesics, and it shouldn't be necessary. So that's the end of the talk, where I apologize for the fact that in some sense this project didn't go as far as it should. The next step, I will try, maybe you will try, is to make this work when the thing you're trying to concentrate on is directly the fractal, as opposed to realizing the fractal as a limit of nice hyperbolic things. And then you actually would like the width to go to 0 as, let's say, the fractals become larger and larger, closer to the whole math. So thank you, and I'll end here.
I'd like to thank Lior. I think we have time for like 1 or 2 short questions. Can you realize Bunimovich stadium as a submanifold of something, let's say in dimension 3, and then have these eigenfunctions by Hassel times something in the transverse and have them localized to that?
Yeah, I don't think so, because I don't think, I mean, the Bunimovich stadium is flat. So I don't know, I mean.
Put it in a box.
Yeah, so I don't know if you could realize the Bunimovich stadium in such a way that things will be hyperbolic of the Bunimovich stadium.
Yeah, okay.
I mean, probably, I mean, I guess you can in some way, but you need things to be hyperbolic in the perpendicular, right? You need that if you have 2 things, which is one on the stadium and one is near the stadium, as you flow on the stadium, they will diverge.
Yeah, but I think you can have, you know.
But if you could do that, then you
can have like a plane of symmetry through, anyway. Yeah.
Yeah, if you could do that, then yes, you can make that happen.
Okay.
You don't need hyperbolicity on the stadium, right? Right, I never use the hyperbolicity of M. I just use the fact that there exist eigenfunctions that do various things.
Are there any other questions?
I have one. How much control do you have on the support of this defect measure mu? Do you know that it's on the totally geodesic submanifold or in the neighborhood of it, or could you have a piece somewhere else?
So it depends on which part. In the first part of the argument, I have complete control. It's exactly on the submanifold. And what measure you get in the submanifold, it just depends on which eigenfunctions, or you can even take approximate eigenfunctions on the submanifold and take whatever limit they have, right? So take the submanifold, take a sequence of eigenfunctions or approximate eigenfunctions on the submanifold. Whatever weak star limit you can get from that, that will be the weak star limit, right? Basically, I'm saying whatever limit you get there, you can do something in the perpendicular direction that won't hurt you and will get you the same thing on the big map.
But when you do that, then so you're then working with an effect measure whose support is in a neighborhood of your submanifold.
No, it literally is in the, I mean.
Oh, so you can really extend the okay.
I mean, okay. So for any particular step, kind of any particular quasimode you construct, its different measure may be supported everywhere. I was saying the weak star limit is supported exactly on the submanifold.
Perfect. Okay. Thank you.
All right. So
but you cannot do this with an actual. This first step that you're doing in this construction, it has to be quasimodes. They cannot be eigenfunctions, right?
Well, on the submanifold, you can take quasimodes or eigenfunctions. But when I try to extend it for the submanifold to the whole manifold, they become quasimodes.
They become quasimodes.
I don't know how to disprove QE.
Okay, perfect. Thank you.
Okay, so Lior, could you stop sharing the screen?